Welcome back. So we're talking about center of mass in this lecture. Before we can actually go ahead and calculate or start to calculate the moment of inertia, which is this idea of almost like a rotational mass or a rotational inertia, we need to talk about a different measurement. We need to talk about this idea that I can condense an entire object down to a single point and talk about how that point moves. Really, we've been doing this in the background this entire time. Anytime we draw a free body diagram, we're placing those points on the object's center of mass and talking about how the center of mass actually translates through space. So anytime we actually talk about translation, we're talking about how does the center of mass work. Now, center of mass is this idea that I can talk about its biased center, right? How does the distribution of mass in an object actually shift where the quote-unquote center of that object is? We're not talking about a geometric center anymore, right? We're talking about this weighted center, literally and figuratively, right? We're weighting the calculation of the center by the mass distribution. So how do we do this? Well, let's consider a general object. And it doesn't need to be a nice, sphere or box or anything particular. It could just be whatever, right? And let's say I have a little bit of mass here, a little chunk of mass. We're going to chunkify our object into bits of mass, right? And I'm going to call this mass I, little mi, right? Because I don't know how many of these little masses I have, but it's a lot of them that make up this one object, right? If I think about where the center of mass actually is, and we'll calculate this in a second, I can talk about the distance of mi from the center of mass as ri, right? And we're using r here because it could be x, it could be y, it could be z, it could be all three of these. Really, r is more of a vector, so we're trying to be a little bit general here. Sometimes I will slip into saying xi or something like that, especially if it is a very simple system only in the x direction. But I want to start off general, all right? So this is kind of what we're building up. Now, if I look at all of my little m's and all of the distances from the true center of mass, right, I can start to calculate where that center of mass actually is. If I say r center of mass, that's going to be equal to m1 r1 plus m2 r2 plus m3 r3, and we can continue going on until we get to, mi ri. And that's all going to be divided by, since we're weighting by the mass, we're going to divide that by m1 plus m2 plus m3 ... plus mi. So in terms of series, right, and sums, what we're saying is that this is going to be 1 over the total mass of my object times the sum over I of mi times ri. Really, again, this is a vector, but I'm not really drawing some of these vector hats just because that would be a little tedious. This is so general, this definition of how to calculate the center of mass, that it's almost not really useful. Like I said at the end of Lecture 1, I want to say this again now. By and large, we're going to give you very, very simple systems to calculate the center of mass of. And part of that is just because this sum becomes very hard if we have a very complicated system. It gets very complicated fast, right? In general, if we have a continuous object, right? Let's say, I'm going to bring back our candle, right? If we look at where the center of mass is this, then I really need to not think about a discrete sum. I'm really talking about, right, 1 over m times the integral of r dm, right? We've taken infinitesimally small chunks of mass here. We're actually integrating over it. So that is more general, right? This is even more general than our general first first expression. We'll give you very simple systems to find the center of mass in, or we'll just give you the center of mass. I'm going to do a kind of a lecture 2.5 where we do a really quick example to show kind of what a simple system would be. But what's the significance of the center of mass? Not only is it a weighted center point on our object, but it's the point about which we would rotate if we don't have any other external pivots. That's a weird way of saying that if I have not aligned forces, let's talk about, I don't know, something weird, right? Something weird. Just looking at this, the center of mass would probably be somewhere-ish around there, right? So if I take this and I place a force here and I place a force here, I'm going to, and say they're the same force, right? Same force. The center of mass won't actually move, but everything will start to rotate around the center of mass. Okay, everything will rotate around this center of mass if the forces are equal but not aligned. All right. So the center of mass is a natural pivot point. Now, of course, you could have an external pivot point. I could say, okay, but I'm pivoting around this spot, right? Well, if I'm pivoting around this spot and I have these unequal forces, yeah, I will still pivot. I will start to rotate around the pivot point. But lacking an external pivot point, the center of mass is how you rotate about. That was a bad sentence. The center of mass is the point with which you rotate about. Now, the center of mass, I'm going to have to do some cuts on this. Center of mass is where you rotate about if you don't have an external pivot. All right, that's the big key point. So it's a really important point, right? It's a really important point. It also determines how we talk about translational motion. So the center of mass is a key point. Let's stop the video here and move on to lecture 2.5 and just really talk about a quick example of this. Before we do, though, the last thing I want to say, and I'll put this on the screen now, and I'll put it in a link in the description. There's a fantastic illustration of this, of how mass distribution actually affects the center of mass using an Airtable and a spinning triangle. It's really great. It's a great short video that I think supplements well, and I would have shown it in class anyways. So so take a look at that. But yeah, let's pause and quick do a small example of how to calculate a simple system's center of mass. All right, see ya.